Thank you for coming to this session. My name is Joshua Robinson. I am from Pure Storage. And today I'm going to talk about how we avoid drowning in logs. What this really means is I'm going to talk about an internal use case that we have for processing large amounts of log data and making sense of it and getting value from that. So to start with, the log pipeline that we built, 2 million events per second we process 24 hours a day, 5-second SLA, and we process a little under a petabyte of data per day. So just to orient you, I'll talk about why we built this first, what business problem is it solving for us, and then how we built it, what technologies we're using. Spoiler alert, it's a lot of Kafka and Spark. So starting out to motivate the problem, we're a storage company. We sell the hardware. I have a software engineer, and don't tell the hardware guys I said this, but software is really the hard part. It's really the most important part of what we're doing. We're building software. We have multiple different products. We have multiple different releases. We have a lot of software that we build. And because it's storage, we have to build software that's really reliable. Because a bug that happens 1 in 100,000 times that might lose customer data is way too frequent. Because that means we will lose customer data somewhere. So we have to be really diligent about how we test so that we don't release bugs into customer systems. Because we knew this when we were started, we invested really heavily from day one in continuous testing. So we have a pretty sophisticated pipeline. Every time a developer checks in code, they do a git commit, we have a series of stages where we compile, we run simple unit tests, and then we push it onto hardware after it's met certain criteria. We have a lab, lots of test hardware. We run tests all day, 24 hours a day. Because again, a lot of possible bugs are race conditions that happen rarely. We built this system so that we can utilize all of our test beds efficiently. We have multiple different release branches, and we have to coordinate which release branch, which part of the code gets priority in running the bigger tests. I'm not going to actually talk about the system we built to coordinate this. What I'm actually going to talk about is a system we built to make sense of all the results. Because if you run 100,000 tests a day, but don't look at the failures, what was the point? But when you have hundreds of thousands of tests, that's a lot of data to look at when you have failures. So that's really the motivation of what our problem comes from. To give you a little perspective, when we started our product about 5.5 years ago, we were a small team. We had one branch of code. We had a few test systems in the lab that we scrounged from somewhere. And we had basically 100, 200 tests that were running per day in total. So our solution was anytime a test failed, we emailed the whole team, and then somebody would say, oh, that was probably me. That looks like probably my bug. I'll go fix it. We were in our whole office was half the size of this room here. That works, but unsurprisingly, this is not a scalable solution. So fast forward to about a year ago when we started this project, we had over 100 software engineers working on this product. We had a lot more test equipment, VMs, test hardware, load generators, simulators, and we had a lot more branches of code. We had a lot more features as well. So what this means is we have a lot more tests per day, 70,000 tests a year ago. Now, we actually got our failure rate down to what I think is a pretty good number, 1%. But when you're running that many tests, that means you still have 700 test failures per day. And we believe that we need to look at every single one of those test failures because every single one of those could be a serious bug that we need to understand and fix. We did some back-of-the-envelope math that said it takes a person, a human being, about 15 minutes to look at a test failure. Look at all the logs, look at the various components involved, and say, I've seen this test failure before, or this is brand new and I think this team should be the one that goes and triages this and fixes it. So continue the math, and you see we would need a team of 20 full-time software engineers whose only job is to triage test failures. Now, one, this is a terrible job. I've done this job before. It's really not fun. But more importantly, this is expensive. This is 20 full-time software engineers, salaries you're paying, and this is in the Bay Area, who aren't actually making anything better. They're not adding features. They're not making your product faster. They're just keeping up with the bug backlog. So not a good use of resources. And of course, we hope all these numbers on the left will double in the next year, so we know this is only going to get a lot worse. Now, the key observation that enables the whole log pipeline that I'm going to talk about later is, of those 700 test failures, only roughly 25 or to 30 of them, on average, are unique. The rest are duplicates. So if you think about it, I check in a bug, I have my code runs on a dozen different systems before I fix that bug. So it triggers multiple different places. But half the bugs are actually infrastructure bugs. This is a real data center, a switch goes down, a VM hangs for some reason, and it takes out an uncorrelated set of tests because they're all attached to the same physical infrastructure. Usually somebody misconfigures something on accident, human error, but it's really only one root cause that could take out a whole rack of infrastructure, for example. So our thought was, could we automate detecting all of the duplicates so that we only needed a much smaller team, maybe 1 or 2 people, to look at and understand the unique failures, but not the duplicates. This would be a huge win for us. Ideally, no humans involved. Step 1, as with I think a lot of AI projects, let's make the human much more efficient with automation. So, our dream, given this setup, was 1, let's automate triaging of the duplicate failures. Simple enough. 2 was, actually, we're running all of our test systems in interesting ways. Let's collect and make sense of all the performance metrics we have. We're actually testing our systems in a much more, let's say, abusive way than any of our customers do. It'd be great to find out how they handle and how they respond to these kind of conditions. But further than that, the log data is interesting. And we can't really predict what our software engineers, the end users, our customers in this case, are going to want to do with these logs. As an example, we have an engineer who made a change to a feature, garbage collection, let's say. They want to know, in the last week, is garbage collection being triggered more often or less often now that they made the change? Is it doing what they thought it was going to do? That's kind of an ad hoc query that we want to be able to answer, but we can't predict what kind of queries our end users, the software developers, will have. So logs, as in most cases, are useful, but in unpredictable ways. We are engineers, and so we want to do all of this in a scalable system. Otherwise, in 9 months, we'll be redesigning this whole thing instead of making it better. And then finally, this does need to be real time, because the turnaround time between when a bug is introduced and when it's fixed is critical for the overall health of our test beds. If we don't fix the bug fast enough, then most of our test beds are sitting in a broken state because of that bug. So we can't do this batch once per night kind of stuff. It needs to be real time. 5 minutes, 2 minutes, that kind of real time. And in general, with log analysis, what we found is, in our case, but in other cases that we talk to with customers, is you tend to see this volume value curve. And what this really means is there's a small number or small percentage of your logs that are super valuable. You know they're valuable, you build reports, you build dashboards, you alert off them, but it's usually a small percentage that's obviously valuable. But you have a whole large volume of logs that's ambiguously valuable. And what that really means is there's some value in there, but you can't predict ahead of time which parts of those log lines will be valuable. So you want to save them, but it would be really expensive to index all of that because you're not going to need 99% of that volume of log data. And then, as we found, you build alerts, you take action on that small, really valuable head. For example, when our software crashes, we put out a stack trace, obviously very interesting. But then as you go further, you start to find other data, like performance metrics, that you want to add structure to, because you know it's valuable in a more structured way, like a time series graph. And further, there's more data. You start to discover that you actually have some amount of value at the head of your log volume. And then you proceed even further, and maybe that percentage of the volume that you know is valuable grows. But that's a learning process as you understand your data and you build out your first initial use cases. So when we start to build a log analysis pipeline, we thought about how to build a generic log analysis pipeline. So of course, the first part is your log sources. In our case, it's all of our test equipment. It's our hardware, it's the load generators, it's the VMs, it's our test coordinator, Jenkins. All of that produces logs data. The first thing we want to do is augment that data and centralize it. So we basically collect all of the log data in one place. And when I say augment, what I really mean by this is we want to add enough metadata to the logs so that we can join across different sources. And a lot of our tests, there's multiple components involved, each having its own different format of log line. Well, when a test fails, we want to know what's happening in all those different involved components. We need to join. That's what I mean by augment. Storing the data, that's straightforward. Store all the logs so that we can later do searches on it if we desire. At the end, we have all of this application-specific machinery, use case-specific machinery, where we're looking at our time series data and where we're doing, in our case, this duplicate detection logic. So at the end of it, we know what we want as an output. And this part, this half of the screen, this is really the part that's specific to our use case. It's the customized part of the pipeline. But just storing the data and then getting it into this useful form requires something else. Something's missing here. And what we want is an index, basically a way to usefully access all of that log data. So a lot of times, first step, and this was true in our case, was to put it in a search index like Elasticsearch. So we put all the log data, this is in a much smaller volume, and then we use Elasticsearch to play and experiment and understand. But this is expensive because we're indexing all of this log data. So pretty quickly, we came to the point where that step, that indexing all of the log data, becomes the bottleneck. In our case, it was really computationally expensive to do all of this indexing, only for us to not look at most of the log data. So to get around that, we built a streaming pipeline. So this is where Spark Streaming comes in. And we put logic in our streaming pipeline to filter out log lines that match our duplicate detectors. And when I say duplicate detectors, think of that as a fancy regex matcher. That's what we're doing when we're looking for these failure signatures. So we have this log index, or streaming pipeline that feeds our index now. So we don't index all of our log data. We only index the log data that matches our filter. Basically, the log data that's associated with test failures, not all of the successful test runs. So that's a clear win there that we're now really shrinking the set of data we're indexing. But what's really interesting is sometimes there's data within that raw data that we didn't filter that turns out to be useful. The way we think about this as is it's a mistake. It's data that we wish we had filtered if only we had known better. Maybe a failure comes up and it turns out we're not looking in the right components to really understand why that failure happened. It's a new class of failure. So what we also really like to do is re-filter the existing data into the index. And this is what gives us the ability to effectively have a do-over. So we get to re-index historical data as though we'd been indexing it in the streaming pipeline all along. Using these two techniques of streaming pipeline with a filter and the ability to re-index on demand, we can much better control the amount of data that we index. Because remember, the indexing is expensive because we're building a search engine on top of some subset of the data. But it's a subset of the data that is really useful, and we want to be able to access quickly and efficiently. So at the end of the day, this is what our log pipeline looks at like diagrammatically. So we are storing all of this log data. So this becomes a really important part of the infrastructure of how we ingest and keep all this log data. And of course, we are a storage company, so I think no one's going to be particularly surprised about how we solve that problem. But I think the other parts of the of this diagram are more interesting. So I'll talk about how we solve these different boxes. So the first is we use our syslog to collect and augment all of our data sources. This is just remote syslog, and it works reasonably well. So our syslog writes a copy of every log data it collects, but it also passes it into a streaming buffer. Again, this was the part that was the least surprising. This is our product. This is where we're storing all of our log data. This is a nice case of dog fooding, if you know the expression, where we're using our product to make our product better, which is deeply satisfying to me. The streaming buffer, we use Kafka. So all of the log lines go through Kafka, and we really use it as a message queue. And so that helps us handle slowdowns, outages, upgrades, changes downstream. And Kafka gives us a really easy way to make sure that we see every log line once. The filtering is done with Spark streaming. So this is where we are doing ETL to put our log lines in a somewhat structured format. And we're doing that matching of duplicates, failure signatures. We also use Spark for the refilter in batch mode. And this is where we're able to basically use the same code as the streaming pipeline uses, but targeted at the resting set of data to refilter. So basically rerun the filter with different conditions and put that output in our index. The index actually, I think, is the most surprising and unusual way that we've solved this particular part of the pipeline. We actually use our product again here. So I didn't really talk about our product. I'm not going to talk about it. I'm going to talk about how we use it. Our product is a file system. We're using a file system as an index. So I'll talk more about how and why we do that. But that's how we're building an index. So instead of a special purpose index like Elasticsearch or a database, we're using a file system. And then all the stuff on the right, gotta point the right way, custom Python code, hooking into Grafana, Influx. This is all of the part of our pipeline that really deals with our specific problem of detecting duplicate failure signatures and creating those signatures once the human has understood the failure. So I'm not going to talk too much about that because I think it's, frankly, just really custom code that is mostly interesting to us. So that's what our pipeline looks like diagrammatically. Now, as I said before, we're actually using a file system. Our product is a scale-out, high-performance, all-flash file system for the index. So now let's zoom in on that and talk about actually how that works, why that works. So we use a file system directory structure to encode all of the metadata of an index. The first part of that is straightforward, the raw data. This is the data that our syslog writes. This isn't an index, it's indexed by time. But it's most straightforward. We just write the logs with a directory structure that encodes the year, date, time, and the name of the device, the host that it's coming from. And this gives a human a reasonably easy way to navigate and look for the log data. And this is produced by our syslog. Again, this is the straightforward part. The second part is how we store the indexed data. And again, we use a directory structure where the pattern becomes the directory name. So we can look up the matches for particular patterns. The pattern basically is, in our case, the bug number. We use Jira. It's basically the Jira number. And then you can look in that pattern and see all the instances of that particular bug because of this file system index. Okay, so it seems straightforward. Now, the reason why this works is because of the characteristics of the file system. So again, we are a flash-based system, so good latency, under a millisecond for most query operations. So you can list directories, you can stat files, all that under a millisecond latency. That's important. But the challenge with using a file system as an index, or even really as a database, which is what we're doing, is searching for data is slow. So your tool, when you're using a file system, is a file system like tool, like ls. That's how you do a query. ls is really slow because ls is single-threaded. ls does one thing at a time when it discovers your directory tree. This is slow and inefficient. This is how software was built 30 years ago, or even older. I don't know how old ls actually is. So what we need in order to do this effectively is to make the tool parallel. So our solution was actually to skip the kernel and the default file system client and use libnfs and create our own custom client. With really the only difference being that we do a lot of things in parallel. So you can think about this as we wrote a parallelized version of ls. And because of the characteristics of the file system, we are literally 1,000 times faster than the single-threaded ls. And that's what enables us to do queries responsively on the metadata that we've indexed. So when someone wants to look up the number of instances for a particular bug, because they, for example, want to be able to prioritize, hey, this bug happens all the time, so let's fix it fast, versus this one is infrequent, so it's not as urgent. We can do those queries in reasonable amounts of time with this client. In reading the data, we can use just traditional pipeline approaches to hide the latency. So we can pipeline the reads, and you can read back that log data very fast. So it's really about a file system can be an index as long as you have the right tools. On the client side, you need to be parallelized. On the server side, you also need to be able to handle a lot of file system queries in parallel. So that's why it works. And for us, it's much simpler than standing up a separate and managing a separate search engine or database. We already have the file system, and from a logical management perspective, a file system is relatively easy to manage. So another view of the pipeline, just to show you the resource allocations here, are our syslog server now, this is a more recent snapshot, handles about 120,000 tests per day, and it's reading in 24 terabytes per day of raw data from all the devices. Most of that data is actually logs from our products that we're building. And we run all of these applications like our syslog, Spark, and Kafka in Docker containers. Our syslog, as I said before, is writing to a shared storage point so an NFS file system, happens to be our product, but is really just a shared storage system. The next part of that is the streaming pipeline, where Kafka and Spark process and filter and look for the duplicate signatures. And the first thing you'll notice here is that data that went from 24 terabytes a day is now 72 terabytes a day. And that's really because of the metadata we need to add to each log line to augment it. And this is, again, where we need to add a little bit of extra metadata so that we can join. So we know where the log line came from, what test was happening at that time, and then we can later make sense of different log lines from different components. And Spark streaming works very well. As I said, we originally didn't have Kafka. We would come in on a Monday morning, realize the pipeline had been down all weekend, and we were dropping log lines, and they were lost forever. Kafka was originally brought in to solve that problem, but it's also just really helpful because sometimes the Spark cluster goes down, slows down, or crashes, because that's what we're doing as software engineers. We're updating that code in Spark. And we introduce bugs there, too. And then, of course, a much smaller set of data goes into our custom code, into our indexes. And that's really the data that's associated with the test failures. That all plugs into Jira, Jenkins, Grafana, all of our bug tracking and test coordination systems. As this is going on, we're also doing the batch mode operations. So this is where we have both streaming services and batch services on the same platform, and it's part of the same pipeline. So this is the refiltering that I talked about earlier, but it's also, when we're building a signature, we say, okay, now I understand this test failure, and I think it's this combination of log lines that tell me this is that failure. Well, the first thing I do is I run a test before I check in that signature, because sometimes I'll accidentally match the whole world if I didn't write a good signature. So we have look-back jobs that do batch operations at the same time as the streaming pipeline. And that lets us have a lot of flexibility to reuse the data and to more reliably check in good signatures for detecting duplicate failures. And I give you an idea of the volumes here. It's about 200 terabytes a day that's read in the batch operations. And then finally, there's a second set of batch operations, which are the ad hoc queries that I mentioned earlier. So sometimes we have a developer who creates a PySpark notebook and wants to run some queries over that log data. And this is more ad hoc and impromptu, but it's still giving our end users, the software developers in this case, access to that log data. Now, the log data is not indexed, so they don't have as real-time kind of lookup access they might want. But it's the trade-off. We keep the data in a cheaper format, so they can still run their queries, but they don't have the ability to access real-time indexed data. And that trade-off has worked for us because the volume and the amount of resources required to index all of that data was far more than those 20 full-time software engineers, so it wasn't practical for us. So the pipeline that we have now, I'll talk about some takeaways, is really our first step towards an AI pipeline. So we've automated probably 19 of those 20 people's jobs, all the duplicate detection, but we still have a human in the loop who needs to generate the signatures. Well, that's step one, and there's been tremendous value in that. I know that because every other day, somebody complains about why their signature wasn't detected. So it's definitely being used by our software engineers because they complain when it stops working or doesn't work as they expect. And now we're looking at how we can use machine learning to further automate that. And we'll see if that works out for us. So can we automatically generate the signatures? So the lessons we've learned in building this pipeline really are, first, index only what you know you need, but store the rest of your log data. And this is what I was talking about earlier, where don't pay the price of indexing all of that data if you're only using a small portion of it, which seems to be a common use case, not just ours. Optimizing for throughput instead of latency creates much more scalable systems. So everywhere we could, we've built concurrency into the system. We're doing a lot of things at once, like, for example, the directory listing operation. If this focus on concurrency and throughput has led us into a much more scalable system, where we're not focused on latency of any individual operation. We're focused on the total number of aggregate operations we can do, and we can scale that out better. And then finally, by disaggregating our storage with all of our applications, it's much easier for us to build out a pipeline like this. So I've shown you the pipeline that we built. What I didn't show you was all the pipelines that we tried to build along the way. We made a lot of mistakes. We changed a lot of things. I kind of alluded to the fact that we added Kafka because we learned that we needed it. We made a lot of other changes as well. We scaled the applications as we grew, and that's all much easier when it's as simple as creating another Docker container or starting up and adding another pod to our cluster. And on the storage side, we started off with a small system, and as we've grown, we've just added more capacity to the system, and we can do that on a different schedule as we're changing our applications. For example, if we decide it'd really be worth keeping twice as much historical data, or keeping historical data for twice as long, it's straightforward and easy for us to do that. So these are really the main takeaways from our pipeline building experience. We've learned a lot as we've made a lot of mistakes, learning about both the applications, but also more importantly, learning about our data and how we could actually effectively make use of that data. So with that, it looks like there are 2 microphones here. I assume they're on. If anybody has any questions, I would love to take them. Yeah.
Hello. I have 2 questions actually. The first one is the data format that you're using in order to store your data, and if you're using also any compression codec, and if you have like benchmarks or performance optimization with the format and the compression codec that you're using.
Right. Okay. So the first question was the format we're storing the data in. So all the raw data is stored as text files. And we use the file system directory structure to encode the metadata about the raw data. For the processed data, the smaller set that we're filtering, we're using Parquet files. So we have some structure to that output log data. The next question I think you asked was about compression. So we actually have the advantage here. I guess this is a subtle plug. The product actually does compression inline. So we don't have to worry about compression because the storage system that we're using and building does the compression for us. So we're storing, I think, on the order of about 7 petabytes of data, but it's only taking up about 1.5 petabytes of actual space because of compression. So the codec that we're using internally in our product is not gzip or bzip. It's more like an LZO or a snappy. So it's more focused on not compressing quite as deeply, but not having the performance penalties of something like those gzip kind of codecs. The clients that we're using. So the applications like Kafka, Spark, and our syslog are using the standard NFS client. So just nothing special, nothing different. Every Linux kernel includes this. So it's basically as common bread and butter kind of stuff as you can imagine. But for querying the database, we have a custom client where we've written using libnfs, which basically allows us to issue our own file system operations. And that's really in only one part of the pipeline where we're querying that metadata. And that, if you remember, I kind of pointed to the right and said, this is all our custom code. it's in there. And then I think you asked another question about performance numbers. Is that correct? Or performance tricks? Yeah, so in terms of what we've noticed is really moves the needle in performance, I would say that the tools that we're using now, Kafka and Spark, are good tools. We're very happy with them. We used other tools previously, which were much less efficient CPU-wise. I won't name names. But the biggest factor we see now in performance is actually with Kafka. And it's not Kafka's problem, it's actually the number of times we're copying data around the network. So when we're processing this 72 terabytes a day, we're actually needing to copy this data multiple times through the network. Once our syslog is bringing it in, once over to Kafka, and then once over to Spark. So just putting all of the raw data through Kafka is actually just a lot of overhead on the networking. So what we're doing instead is converting the way we store data in Kafka to storing pointers. Because we're writing the data down anyway. So instead of putting the data through Kafka, all the raw data through Kafka, we're putting pointers and saying updates, pointing back to the full data set. And that means Kafka is going from processing 72 terabytes a day to processing gigabytes a day. And so it dramatically changes the load on our network. So that's really, and again, this is problems that we've come to at scale, now that we're operating at 2 million events per second. That's the performance problem that we're today dealing with. Any other questions? Yeah. So our storage internally is doing erasure coding. So we're doing read solemn encoding, protecting the data. It's an enterprise storage system, so we're protecting against data loss of 2 components. That all is handled internally by our storage, yes. I'm happy to talk a lot more offline about what our storage is, but I'm also happy to talk more about the pipeline as well. The pipeline? Or the... No, we don't. Well, that's not the first time we've had that question. And it's, to be fair, we took this exercise very much as a, let's put ourselves in potential customers' shoes and do what they would do. So we tried to think about this not just as our own engineering organization locked in a corner in cubicles. And we're learning about which parts of it are very general purpose and which part of it, are very special purpose. And all I can say is it's an intriguing question that we're thinking about.
One more question. What is the bottleneck right now, and how you are going to scale next years?
So the bottleneck is the Kafka issue I just talked about. It's absolutely that issue. And it's really just the number of copies made over the network is the issue. The next issue actually is our syslog. Our syslog is not quite as reliable as we would like. It drops, an order of 1 out of every 1 million log lines, which is starting to be a bit of a pain point. That's not a performance issue. That's more of a, making sure that we're seeing every log line once issue. But the performance issue is absolutely the Kafka, which again is not a problem with Kafka. It's just, because actually Kafka has been probably the most reliable and easy to use part of the whole thing. Yeah.
You're using Kafka streaming for the streaming part. Have you considered using Kafka streaming or Flink or Leaf?
That's a good question. So obviously we started, and this is a bit more of, where we're coming from is we had more experience with Spark. So we started more of a Spark-first approach with the pipeline. And we added Kafka later, and so Spark was already doing that responsibility. And it's true. So there are multiple tools that could also do that role. And we've only started doing proof of concepts. Because we're in this trade-off where we want to make the pipeline better, but we also want to experiment with different ways we could have built it. And right now, we're still focused mostly on making the pipeline better for internal users. So the short answer to your question is we have not looked in detail on the other options. I think this comes to a case where anytime you're building a pipeline, there's a dozen different ways to do it, all of which are probably going to work. But from our perspective, at least, we started with what we had the most experience with because that helped us get to the point from, hey, this is an interesting idea, to proving out that this is going to work. Because I think it probably is common use cases, or common cases, we need to justify the time and resources we're spending on this. And so for us, proving that it will work as soon as possible was really important, because that way we could actually keep engineers staffed to keep working on this. So we picked tools that we were most comfortable with. Question in the back?
One last question, which is, how many number of users you have on this in terms of actual active users, users that you service? That's number one. And number two is, have you tested out sort of throughput and latency time?
So the number of active users is our set of software engineers. So that's about 100. Of course, on any given day, I would say only 10 of them are actively using the results on average. So the user set is small, but again, that they're doing a very critical part of work for our infrastructure, which is making sure we understand all these bugs. We're in the process of expanding this pipeline to the other development team, and so that will triple our user count. Your other question about latency and performance, we have an SLA that we need to be processing all of the log lines within 5 seconds. And for the most part, we stay within that SLA. So that's really what we optimize for, is not falling behind more than that length of time. Thank you, everyone. Again, I'm happy to answer more questions. If you're interested in learning more about the product, come get an espresso downstairs. We're sponsoring the espresso machine and ask questions. Thank you.